Okay, so welcome to session 2, talking about containers and algorithms and the standard template library. Before we start, a bit of an apology. If you can hear, I'm sort of deathly infected with man flu today. So I, as well as running late, I haven't had my usual preparation time. So it's going to be a bit of a funny session today, and we might end up finishing early. And yes, it's not going to be quite as fluid as usual. So apologies in advance, but I'll do my best. And you're going to have to put up with me sniffing a lot. Sorry, what can I say? Blame the germs. So first of all, who's here for the first time tonight? One person. Well, welcome. Nice to meet you. So yeah, we're in. This is now our third module. So we have the courses kind of broken up into little 4 or 5 week modules. This is a module all about parts of the standard library, particularly the containers and algorithms part of it. We started last week, although last week was more of an introduction, so you didn't really miss all that much last week. So if you already know a bit of C++. Oh, okay. Well, excellent. I'm going to stand up instead. Why not? Okay, well, if you have been watching on YouTube, then you'll already know all about the Slack channel that I talk about every week. So there's no need for me to spend too long on that, but please join it if you haven't already. Next notice, Advent of Code. Who's doing Advent of Code? Right.
You said it's very hard.
No, I didn't say it was very hard.
Day 4 is very hard.
No, I didn't say it
takes a long time.
I said it was a lot of work. It's not the same as being very hard.
Both are equivalent. Depends on how long you work, then it becomes hard.
No, it just there's a lot you had to do in order to get the answer. Usually it's quite clear what you need to do. So day 4 required a bit of work, but don't let that put you off. No, Advent of Codes, what are we now, the 11th? Is it the 11th today?
Yes.
Yeah. So it's been going for 11 days, but if you were to sign up now, you've still got 11 days worth of problems you can solve. Well, a lot more than that actually, because they've still got the problems on there from 2015, 16, and 17. So there's lots and lots of problems in there to solve. I really, really highly recommend it. They're really great little exercises. It's not, you don't need any particularly advanced C++. I mean, it's not, you can use any programming language you like. It's not for C++ or anything, but it's a really good chance to practice. And especially for a lot of the problems, the STL algorithms, so what we're going to be talking about in this little module, they come in really handy. So I really, really strongly recommend that everybody go to adventofcode.com, sign up, just have a go at day 1. You've got nothing to lose, right? You're here because you want to learn C++. You want to learn C++, you need to practice. You're not going to get any good at it if you don't practice. And these are an awesome opportunity to practice.
And they're fun.
And they are fun. Yeah, that's why I've been doing it. And if you want, once you've solved it, I mean, don't cheat, but once you've solved it, you want to compare to my solutions, mine that were all up on GitHub at that URL, and Ollie's got his solutions up as well. Might be quite interesting to sort of compare and contrast my approach to things to Ollie's. I've had a look at his code. It's quite different to mine in some ways. We have different ways of going about things. So yeah, really, really strongly recommend. And if you don't do it, then what I'm going to do is set the exercises as homework. Right, so then you'll have no choice.
I'll set them in the workshop as well.
Yeah, exactly. Yeah, no, this would particularly on if you come along to the Thursday workshops, which you really should, then yes, these are really good problems. Okay, so last week we revisited the end of module quiz from the last module because we didn't leave you a lot of time the week before that. And we went through the solutions. Then we had this introduction to the STL. Sort of didn't go into too much detail. It was really just kind of broad brush what the STL is, how it started, and all that sort of thing. Today, well, I'm going to be saying pretty much the same thing I did last week, but more quickly. And then we're going to talk about iterators. So as we'll get into, iterators are sort of the glue that stick together that match the algorithms with the containers, or rather the containers with the algorithms that operate on them. So today's going to be all about iterators. But before we get into that, last week, so who was here last week? 3 of you, 4 of you, and Laurent, who's not paying attention.
I was reading the 11.
Okay. So I didn't specifically set it as homework, but we were working on this exercise at the end of the class, available at this URL. So what I basically wanted you to do was to find the right algorithms that you could use to solve these problems. So the idea was I wanted you to kind of go away and, well, not go away, but get on the web and just have a look at the available algorithms and see what was there that you could use to solve these problems. So for the first one, we had given a vector of words, so I just picked some random words. There are websites that would just give you lists of random words. I had no idea, but anyway. So just given some random English words, can we print them out in alphabetical order?
Facebook.
Oh.
Gives you all the random words you need.
Yeah, and then exercise 2, similar idea. We had a list of random numbers instead of words this time, and wanted to find the minimum and maximum values there, and also the median value of those numbers. So the solutions are, there's a solutions branch on that GitHub repo that I just put up, but we'll have a quick look. So who managed to do this, by the way?
First exercise, but it wouldn't compile. There was a compile error on my window.
Because you tried to use standard min for the second part, and min and max.
No, it just wouldn't compile the actual without me touching anything.
Okay.
So I had that problem with it was reversing standard min and standard max. So I pulled standard min and give me the largest one.
Okay. Well, let's have a little look at it. So I gave you a bit of a setup thing. I included this header library called NanoRange, and this implements. I talked last week about how in C++20 we're going to get all this new really good stuff, and it's going to update what we're currently working with. So this is a library that implements some of that. Just makes writing algorithms go a little bit simpler, a little bit easier. But you could do all of the exercise just using the existing STL. You didn't need to use this. That was just for convenience. So can I blow this up a little bit? A little bit. Okay, so print words. We wanted to print them in alphabetical order. So get words returns you a vector of words in non-alphabetical order. So what do we want to do with that? Sort it, absolutely. So to sort it, we use a function called sort. Fantastic. And you can see in particular with NanoRange, it's really easy. You just do nano sort words. With the standard library, you do standard sort, and then you do words.begin and words.end. And we'll hear today about, yes?
I was wondering if we have to use the third parameter for this to the sort, giving the criteria according to which.
So
because we don't know if it's overloading the inferior operator.
So it's a vector of strings, and by default, the strings will sort in alphabetical order, which is what you want them to do. Lexicographical order, as they say. Yes?
So what if there's 2 strings, both begin with A and AB? Does it go to all the...
Yes, yes. So aardvark will go before, advent or whatever. Yes. So sorting strings will do what you want to do, which is to sort them in alphabetical order. If you wanted to do something a bit more complicated and sort them according to a particular locale. Well, that gets more difficult, but we don't care about that. We're just using plain old English 26 letters. So we sort the words, and then for each word in our vector, just use a range for loop and print out each word separated with a new line. Or if you want to get really fancy about it, you can use a copy function. So I said last week, I told you I'm not really with it today. Said last week that whenever often when you use a for loop, it can be a good idea to sort of think about how you could use an algorithm instead. So we can use this sort of sneaky trick to change our stream, that is standard out. We can wrap it in an iterator and then pass that to copy. This is pretty advanced, and don't feel at all bad if you don't know this. There's no way of sort of coming up with this yourself. You kind of have to be shown it, right? So this thing about copying something into an iterator that wraps up a stream, it's a neat trick, but it's just there to show off. Really.
So is that what you did for printing it out each?
Yeah, so this does the printing, yeah. So what it does is it copies every word in this vector into standard out. And then the second parameter here says we're separating them all with a new line.
I'll take your word for it. I can't see from this part.
Yeah, well, I can try blowing it up a little more. Yes, unfortunately, different room to normal, so we've got these TVs. We've got it in stereo though, so you can kind of zoom each eye individually, and it'll work just well. Work really well. Yeah. So this extra bit, don't worry about that. That was just showing that you can do it in just one line if you want to really show off. But it's if you did this, that's fine. The key part was that you identified that the sort algorithm is the one we want for sorting a list of words, a list of strings, or a vector of strings rather. So for the second part, again I'd already written this function for you that just generates a whole load of random numbers. I think it's 100. What did I say? It was 100 random numbers between 0 and 1,000, or 1 and 1,000.
Did anyone else get a compiler and just trying to run it without even changing it?
Yeah, the nano.
Well, if you don't update MSVC, you're going to run into problems. Always run the latest version, right? So we have this really nice, again, the C++20 stuff. There's this function min-max that just does exactly what you want. It returns a struct that contains the minimum and the maximum in that set.
Is it a pair?
Sorry?
Is it a pair it's returning?
A pair?
Yeah.
No, it's a special struct that's called min-max result, or min-max result t. And it has two members, one called min, one called max. And then you can see we just print, I've created a new object called min-max, and we print min-max.min, which is the minimum, and min-max.max, which is the maximum. So this is a really kind of nice way of doing it, or will be in C++20. For the existing STL, if you're using that, there's a function called min-max element, which is a good way of doing things. So min-max element is the way you do it in C++17, and that will return you a pair of iterators. So then you have to dereference the iterator in order to get the value. If you don't know what that means, well, stick around, because that's what we're going to be talking about today.
It's just an aggregate, right?
Min-max is, yeah.
Can you explain line 28?
I could have used structured bindings, in fact, yes. Sorry.
What is line 28?
Line 28. So this calls the algorithm min-max.
Right.
And min-max is an algorithm that returns you both the minimum and the maximum element in a single pass. So
Of that array or
of that array. So numbers here, I've used auto, but it's a vector of ints is the type. So this just goes through every value in the vector and finds the minimum and the maximum value using the default comparison less than.
Okay, cool. Thank you.
Finding the median is a bit trickier, a little bit trickier. So there's a function called nth element, or an algorithm called nth element. It's what's known in computer science as a selection algorithm. And what this does is it does sort of one, you can think of it almost as doing one part of a complete sort. So it takes a particular element and it puts just that element in the position it would be if the whole range was sorted. So if the whole range is sorted, every element is in its right place. What nth element does is it takes one element and puts that in the position it would be in the complete sort, but it doesn't sort the whole thing. Because sorting a whole container is quite a time-consuming operation, or it can
We
be.
need to do that to identify the median on that middle element.
So the median element is the one, if the whole thing was sorted, the median element would be the halfway point.
Yes. But would it need to have sorted it to know which was the median?
No, you can use this selection algorithm, which says, given the element in position size divided by 2, put that in its right place. Don't worry about sorting anything else, but just put that one element in its correct place. So this is kind of that's why I said it was harder, because again, it's not something that would be easy to come up with by yourself. But I was hoping people might go away, go to Stack Overflow or whatever, say, how do I find the median of a list of numbers in C++? And they might find a website that says, use nth element.
Is it like an efficiency thing? That's why they...
Exactly. So you could solve this just by sorting all the numbers and returning the middle one.
Yeah.
So
That
we've
would-
done that before, in like week 2 or 3.
Yes.
But I'm not getting this.
Yeah. Okay, so sort would be fine. That's going to put all the elements in their right place, all 100 of them.
Yes.
What nth element does is it just puts the middle element in its right place.
Yes.
Because that's the only one we care about. We don't care about whether the rest is sorted. That can be in any order we like. We only care that the middle element is sorted. An nth element just does that, so it operates much more quickly than a full sort.
Just out of curiosity, though, say if the median element was right at the end,
Yeah.
would it still just take as long anyway, sort of technically?
No,
Have
it's
to go-
it's much cleverer than that.
Okay.
Yeah. Yeah.
The median, if it's an even number of elements.
Yes, that's true, but I didn't want to worry about that. Just take the one before the.
So how does that does that? Does it like compare them and find out where the middle one is? Not actually sorting the list. Surely this is mad consuming.
Sorry.
It's resource intensive in its sort.
Sorting, the full sort is very resource intensive. It's an n log n algorithm. But doing the just the nth element just does like, so if you think about, it just places one element in its right place. It doesn't worry about the other 99. So it's,
I think where me and my guy, how does it do it?
how does it do it? We could spend the rest of the session talking about selection algorithms. It's, if you're really interested, there's a Wikipedia page that tells you what selection algorithms are and how they work. There's one called Quick Select, which is more or less what the standard library uses. It actually uses something a bit more fancy called Intro Select, but it's basically Quick Select with some modifications.
So line 36 it says, nano begin numbers, which is vectors to say start. What does it begin function with? At start of that vector.
Okay, it's a good question. So in fact, leading us into what we're going to talk about today. So nth element takes, or this version of nth element takes 2 arguments. The first one is the whole range, and the second argument is an iterator into that range. And as we're about to find out, an iterator is sort of like an object that represents an index into a range. So this is saying, I want the element that's at the beginning plus half the size. So size divided by 2. So I said this is 100, so this is going to be element 50. But we're passing an iterator to element number 50.
But why do we need the begin plus the size slash half? Couldn't we just go away with the size number slash half?
No, you need to pass it an iterator. And we'll,
So
today
the
is going to be
begin
all
is
about.
the iterator.
Sorry?
The begin is the iterator.
Yeah, this function returns you an iterator to the start of this.
So that will
Collection.
be 50, and then size.
So no, this is going to return you a special object that's called an iterator that we're going to talk about today. And then it's going to move that iterator so that it, or advance that iterator in the terminology, so that it points to element number 50.
Okay. Thank you.
And then we just access the middle element of this numbers array, and print it out. So this nth element, again, it's something that you kind of have to be told that nth element is something that you can use to find the median. It's not something I would expect you to come up with just like that, but this was kind of the point of the exercise, was to do a little bit of research and find the right algorithms for the right tasks. And again, I'm going to talk about it, bang on about it a bit more, but if you do this advent of code, it's a really good opportunity to do that, because you're given a problem description, say do these things, you can sort of try coding it yourself with for loops and things, and then you might sit back and look at it and go, well, hang on, I could actually just apply find, or whatever the algorithm is. Yes, you had a question, Sam.
Yeah. So
Is it about nth element?
Yes. So you're iterating.
I wish I hadn't done this.
You're iterating from the beginning of the vector, but you're only iterating up to the halfway point of the whole size
No.
of the vector.
No. You're iterating over the whole vector, but we are trying to put element number 50 in its right place.
Yes, but so why is in the syntax of the actual command or code, why is there a plus only the half? I thought you meant it goes up to only the half of the vector.
First argument is everything.
Yeah.
Second argument is an iterator to an element which
So think of an iterator as like being an index into the set. It's saying I want this position to be correct, to have its correct value, as if the whole thing was sorted.
So is that what the last term will statement?
So this is saying this whole bit, nano begin plus nano size divided by 2, that constructs an iterator to the 50th position.
So, in essence, it would be kind of easy to do that, wouldn't it? If you want to algorithm, it's easy. So you just go, is this less than me? Yes, it is. Is this less than me? Yes, it is. And then we'll just add up and see if either side has the same number of things. So that way you don't really have to sort it.
Exactly.
there is a stood nth element.
Yes, there. Oh, yes. Sorry, this is not nth element. As with all these algorithms, and there is a standard nth element. You could use it. Instead of this nano one, the only difference is instead of passing just numbers like that, you'd have to do numbers.begin, comma, numbers.end, comma, numbers.begin plus numbers.size divided by 2.
Allows in the standard library allows you to work on a small chunk of your entire vector if you wish. This is just taking the entire.
No, this does as well. It has another overload that takes 2 iterators.
Okay, that's a simplification.
Yeah.
In the library.
Yes, that's the whole point of giving you the library. So
It's a convenience.
a convenience overload, indeed. That's exactly what it is.
Do you have a struct which returns the other statistical features of one vector?
I'm sorry, can you?
You got minimax,
Yes.
which return. But you have a bigger structure, a bigger struct which returns other characteristics than the min, the max, like the values of that.
No, not kind of built in, not in the standard library, no. Min and max is kind of special because you want those frequently. No, it'd be nice in a way if you just had a.
You don't have statistical libraries within STM?
No specialized statistical algorithms. There may well be in Boost. I don't really know. There are so many Boost libraries that maybe Ollie knows, but. Yeah, I don't know of any specific. You'd have to probably find some particular statistical libraries if you wanted to do that stuff. These are very sort of general purpose algorithms. Oh, dear me. Okay, so algorithms, they can do fancy things. They can do quite simple things as well. Count and find, these are things you probably have written for loops for that haven't really thought about. And realised that there are algorithms. Right up to the other end, the really complicated stuff like sorting, like selection, nth element, set operations, merging, and things like that. And next week, we're going to talk go into a bit more detail about the various algorithms that are available, and I'll also talk about the various containers that are available. But today we're going to talk about iterators, those being the glue layer between the algorithms and the containers. Oh, I forgot to add these couple of slides. Well, never mind. Let's do these again. I said last week, in the early 90s, I think it was 94, it was published. A Russian, originally mathematician turned computer programmer called Alexander Stepanov wrote this library while he was working for HP. It's called it the Standard Template Library, or STL. It's provided a lot of containers, such as vector and list and map and many others, set and multi-set and lots of them. Has some containers and separately a lot of algorithms. 90 odd algorithms, lots and lots of things, like sort, like nth element, like count, like find if, like set intersection, like set union, like partial sort copy. There are lots and lots of them, that's what I'm saying. And really the absolutely key thing that Stepanov did, the kind of genius thing of it, was to decouple the containers from the algorithms. So the algorithms are what we call generic. They're written in such a way using a C++ facility called templates. They're written in such a way that they don't care what type of container they're operating on. As long as the container meets certain requirements, as long as it has certain properties, as long as, in the lingo we say, as long as it matches some concept, then we can use it with the algorithms. And different algorithms have slightly different requirements. But for the most part, we really decouple the algorithms from the containers. So you can write, if you write in STL style, you can write a new container. You can write your own container that is usable with any of the algorithms. Or going the other way, you can write an algorithm that is usable or operates on any of the containers. So they're completely decoupled. And this was the really clever thing that Stepanov did. And it really it coined the term generic programming for this approach, and it really changed the way people looked at C++, thought about C++, changed the language, changed the way people thought about the language completely. And much of what we have in the standard library today was imported directly from this HP library, the STL. There were a few other bits that predate the STL, so standard string and the IO streams horribleness was much earlier. But all the other bits that you've probably used, vector and so forth, those all come from Stepanov's work. So even though STL properly refers to this 1994 library that Stepanov wrote, it's still really common today for people to refer to the standardized parts of his work as the STL, and I do it all the time. So when you hear people today saying about the STL, what they mean is this part of the standard library, the containers and algorithms part. And you sometimes get very pedantic people who will try and correct you, who are really annoying. So tell them that I say they have to shut up. don't, because they're the kind of people who really argue with you. Just ignore them. That's better. So, we said this. We got a dozen or so containers. I've counted them. I think there's about 12 in the standard library, and 90 plus algorithms that work with them. And then there are other things. So we already mentioned Boost. So Boost provides some other different container types that have different properties from the standard ones. And it also provides more algorithms that, for one reason or another, aren't part of the standard library. Perhaps they have more niche uses. But the way this works, the decoupling means that you can use any of those containers on any other, apply any of those algorithms to any of those containers and vice versa, as long as they meet the requirements of that algorithm. So part of what I wanted you to do with that last exercise was to go and look at the algorithms, see what is available, get to know them, get to know the standard library algorithms. They're really, really useful. Because whilst you can go and write something simple like count, you can write that yourself very easily. We had 3 different examples last week of just iterating through a set and counting the number of things that match a particular value. But you don't have to go through and write that however many times yourself. You can just use this standard count algorithm that's already available for you. And then somebody else, when they're reading through your source code later, they don't have to look at that for loop and try and work out what it's doing. They can just see standard count. Oh, okay, this is counting. So even with the simple algorithms, it's an advantage. But then we get to the really complicated things like set symmetric difference, that would be really quite difficult to write by yourself in a way that is both efficient and bug-free. But if you use the standard library version, well, somebody else has gone to the trouble of making sure that it's efficient and that it's bug-free. And the standard library version is probably used by hundreds of thousands, if not millions of people. So you can be reasonably sure they've done a decent job of it. So, yes, use the standard library algorithms whenever possible would be my advice. And actually, if you go and look at my Advent of Code solutions that I put up on the first couple of slides, I've really gone to town with this and use them wherever possible because I was just trying to show off, basically.
I use it too, just within reason.
Okay. Let's finally talk about iterators.
I even to know the whole list of algorithms available. Is there like online
Where
resources?
can you find them? You can go to cppreference.com.
Yes.
CPP algorithm.
That would be a good website to have, wouldn't it?
It's right here.
It's actually a website.
Well, it's good CPP reference.
cppreference.com.
WCPP algorithm.
There you are, which has a page with all of them, and you can click each individual one, and it will tell you exactly what that algorithm does. It will give you a whole bunch of more information besides, including the preconditions, the postconditions, the algorithmic complexity, and for most of them, it's got an example implementation as well. So CPP reference is brilliant.
At the bottom. Examples.
Oh yes, and some example usages as well.
That you can run.
Yes, so CPP reference is brilliant. It's in some ways it's quite dry. It's a bit like reading the dictionary. It is very much a reference site. It's not a tutorial or anything like that, but it gives you all the information you could possibly want. Yeah.
Probably worth mentioning, as someone who's learned other languages, that learning all of the the contents of these libraries is really good to give you like a vocabulary for handling and dealing with problems.
Absolutely, yes.
So that's really where the kind of encouragement to read and it may seem a weird suggestion to go and read all the algorithms in, all the functions in algorithm, but that's why, to give you the vocabulary to
Yeah, so if that didn't come out on the video, it was that learning these, getting familiar with them, it gives you a vocabulary to deal with problems, which is a brilliant way of putting it. Yeah. And again, yeah, sorry.
So I say, I'm just looking at this, right? It's like 120.
Is it 120?
It's something like that.
Oh, I said 90. I've been underestimating.
I'm just guessing. You're probably more accurate.
There's been a lot of innovation going on.
No, I just think, I always thought like when I was trying to learn Java, I tried to learn everything and it's pointless.
Yeah.
Because it makes sense, like it's task-based to learn that. Put that in memory then.
Yeah. So unless you're one of these people who just has one of these memories where you can just read it and recall it years later, yes. Unless you're Rain Man, you're probably not going to go and memorize all 90 or 120 algorithms just like that. But if you sort of browse it either there, or you can find a C++ textbook or whatever your preferred resource is, it can happen that sometime later you are working on a problem and you've coded up on a for loop and you just sort of scratch your head and go, oh, I vaguely recall once upon a time I read something about that. I can't quite remember it, and then you go and look it up again, and then you can find, you can go and look and say, oh, well, actually, I could use standard rotate to do this, or shift left, or whatever the one is that's appropriate for your problem. Sorry, go on.
So a good approach would be like, if you know, deal with algorithms, I would have thought one of the first things we would do is kind of look here and see if anything lends itself for a better solution for yourself, rather than trying to reinvent the wheel again.
Yes, that's exactly another way of doing it. Is, as I say, whenever you write a sort of non-trivial for loop, anything that, there's somebody who's very well known in the C++ world, does a lot of very good talks. It's called Sean Parent, and he did this very famous talk a few years ago, I think 2013. It's called C++ Seasoning. It's the name of the talk. I'd recommend you go and find it on YouTube. And his sort of guideline is that if you have a for loop that's more than about 4 lines, think about whether you should be using one of these standard algorithms, because you may turn out that what you're doing, somebody has already implemented, that you're, as you say, reinventing the wheel. So that's the kind of guideline I use. Is this more than about 4 lines? If it is, I go and browse that and go, well, actually, I could just use this. Right, where were we? Iterators. Iterators. Yes. Okay, so we've talked about algorithms. And we already met a couple of containers. Vector and string, for example. How do these work together? I've said they're decoupled in that algorithms can work on any kind of container, and the containers, they're independent from each other. And the way that they are glued together, the way that they interoperate, is via something called iterators. They're the glue that bind together the containers and the algorithms. So containers provide iterators, and algorithms consume them, use them. So for example, I've got a vector of 5 things. Something you've seen lots of times on this course by now. And then I say, give me an iterator to the first element of this vector. And give me another iterator to the end of the container. And then I'm going to pass those 2 iterators into this algorithm called sort. And this will sort the vector so that after I've run this, the vector will contain 1, 2, 3, 4, 5 in that order, which is what you would expect sort to do.
So
Correct. So this is an important point, actually. Some algorithms have their output elsewhere, and other ones modify the container in place. And sort is one of the ones that modifies it in place. But there's no single iterator class. There's no, not even an iterator interface or base class that you might have in other object-oriented languages. Rather, an iterator is sort of an idea, a concept, a protocol. And something is an iterator if it does the things that an iterator needs to be able to do. And what we're going to talk about today is what does an iterator need to do? What operations can you perform in an iterator? So if a particular type has all these operations and they perform the expected functions, then it is an iterator. It's what we call duck typing. So if it looks like a duck and it quacks like a duck, it's probably a duck.
Dog.
But
Sorry, Mr. Dog with duck.
duck, yes. Dog typing. I'm not sure what dog typing would be. But, anyway, so there's, as I say, there is no one iterator type. An iterator is what we call a concept. And if something meets all the requirements of the iterator concept, then we say this type models the iterator concept. There's going to be quite a bit of terminology thrown at you today. Sorry about that. So, what exactly is an iterator? The very simple answer is you can think of it as just like an index into some collection. So I'm going to use the term collection today because I don't want to use set because that's got a specific meaning. There is a type of container called a set. Some collection, which could be an array, like a contiguous array like vector does, or could be a linked list, or it could be a hash table, or whatever kind of collection we have. Basically, anything that we can put an order on, that is, we can go from one element to the next, can be thought of as being some sort of iterable thing. And an iterator just represents some position in this collection, an index into it. That also knows which collection it's part of. So, Stepanov originally, once upon a time, called these things linear coordinates. So you could think about it's a coordinate into your collection. It tells you where you are. And it's a linear coordinate because it's only in one dimension. Right. God, you're hungry, Ollie. So that's the simple answer. And that's really the way I want you to think about iterators today. Or, well, not just today, in general. It's basically just like an index into your collection. If you want a more complicated answer, well, there are sort of generalization of pointers. So we have this notion of a pointer which contains a memory address, holds the address, holds an address in memory, and you can change the pointer so that it points to a different address in memory. And it's a sort of linear coordinate over your entire memory array, sort of. And pointers are the most general kind of iterator, and we can sort of generalize the things that pointers do to act on specific collections. This is just, don't worry about those last two bits too much. So we haven't actually talked very much about pointers today in this version of the course very much so far. So I probably should have got rid of those last 2 points because they were a leftover from when we did this before.
Is it like a dynamic pointer?
Is it like a dynamic pointer?
What does dynamic mean in this context?
Yeah. Sounded good. No, well, okay. Let me put it a different way. I said that something is an iterator if it meets all the requirements of being an iterator. sounds circular, it's not really. If something meets all the requirements, then it is an iterator. And a pointer, at least a pointer into an array, does meet all those requirements. So a pointer is a kind of iterator. But there are other kind of iterators besides pointers. That's why it's a sort of, in mathematical terms, a generalization of the idea. So that's the complicated answer. But let's forget about the complicated answer and focus on the simple version of what an iterator is. It points to a position in a collection. So we already saw this in the example with sort just there. Iterators, we generally use them in pairs. And almost all the algorithms operate on pairs of iterators. They tell you the position. Remember, an iterator is a position. It tells you the position to start your operation, the position to end your operation. The first and the last. And we say a pair of iterators used like this. They denote a range. And the first iterator in the pair denotes the start of the range. And here's the tricky bit. The second pair denotes one place past the end of a range. This is what we call a half-open range in mathematical terms.
So the last iterator. Oh.
The second element of the pair, second iterator of the pair, refers to one place past the end of your collection. So, do we have any whiteboard?
Yeah, behind you.
Yes, pens. Oh, there are pens there. Yeah. All right. So this represents a vector in memory. It's a vector of 4 things, and each one of these elements occupies a bit of memory. So we can form a pointer. We can get an iterator which points to the start. So when we call begin on our vector, it's going to return an iterator position which points here. But when we call end, it's going to return some sort of phantom value that represents one place after the last element. Like a marker, like a sentinel. Absolutely, yes. So it's a half-open range. What you get from begin is valid, what you get from end is not. That is, you can't go and look at what element is contained here. This points to a valid value, this does not point to a valid value. Okay? It's a really important sort of concept to raise some questions.
What do you mean by valid?
Well, I've jumped ahead actually. We'll talk about what valid means in a couple of slides' time. But the important sort of concept to get from this is that when we have an iterator pair, so the algorithms all operate on iterator pairs, they tell it where to begin, where to end. The beginning value is included, the end value is not included. It's a half-open range. Beginning value is included up to, but not including the end. Yeah?
What can you do with that end value? I mean, can you with the end iterator?
Yes.
That's pointing so the just beyond.
Yes.
The actual end of your vector.
Yes.
Whatever.
What are the valid things you can do with it?
Correct.
We'll talk about that. So this is imagining we had a vector. A vector is, of course, not the only kind of data structure we can have. We might have a linked list. So here's a linked list with 3 elements that's represented each one. A linked list like a chain of things. Each node contains a pointer to the next node. And our beginning value is going to be, again, the first thing in the chain. And end, it's going to return us an iterator to some sort of separate sentinel value that's not part of the chain. It's not a valid element of our linked list. It's just a marker, just to say, you've reached the end. So this is a bit sort of funny and head-scratchy the first time you come across it. Yeah.
Can these both move either direction?
No. It's not.
This end, the start one can only move that way.
Yes.
And the end one just stays there all the time.
Yes. Some iterators you can go over backwards, we call those bidirectional iterators, and I'll talk a bit more about that in the next few minutes. If these diagrams are confusing, don't worry about them too much. Just remember that when we have an iterator pair, it includes the first position, it does not include the last position. The algorithm operates on a half-open range. It does operate on the first, goes up to, but not including the last.
Is this due to how counting works on arrays and vectors?
Yeah, and it basically means that it makes a lot of algorithms much easier and more efficient to implement. That's the reason for it, basically. So typically the iterator pair we'll give it is the entire collection, but it doesn't have to be. Let's say we had a vector that contains 100 numbers. If we wanted to, for whatever reason, we could only sort the first 10 things in that element, in that vector. And the way we do that is we'd call sort with an iterator which points to the first element and an iterator which points to the, we want to sort the first 10?
Sorry, 9.
The 11th, one past the last thing we want to sort. Exactly, yeah, very good. Yeah.
But the first element is 0 element. So you have to go up to the 10th to get.
Okay, yes, element number 0 and element number 10. Yes. Sorry?
It's the 11th element.
It's the 11th element, but it's element number 10 because we count from 0 in C++. It's an error to dereference a past the end iterator. This means that whenever we're at this one place past the end of the array, and you try and say what lives here, can I get the value of the thing that lives here? That's an error. Oh, thank you. But we'll talk a little more about invalid iterators in just a minute. So we can obtain an iterator to the start of the container by using the begin member function. So all of the standard containers have this .begin function. And that gives you an iterator to the start of the collection. And we get an iterator to one past the end of the collection by calling .end. So for any algorithm, if you want it to operate on the whole collection, you just pass .begin, whatever your object is, .begin and .end. And if you don't like member functions very much, there are these free function versions, standard begin and standard end, which basically do the same thing, except they operate on built-in language arrays, C arrays, which don't have member functions. But you shouldn't be using those anyway.
Are they not the same thing?
Sorry?
Like they're not just linked to one to another?
Standard begin will call container.begin for you.
Oh, okay, yeah.
Sorry, is the reason why one is beyond the last element, so you don't want it to reference the same thing? I don't understand
why they've done it. Yeah, so it would have been a valid design choice just to include the last one as well, right? To have a closed range. So up to, from, up to, and including the end. The reason they didn't do that is because it turns out when you get to actually write implementing the algorithms, it turns out that it becomes much easier to implement several algorithms if you have this, what we call sentinel value, the extra value. So yes, in principle, they could have used a closed range. Turns out it makes life easier if you have a half open range instead.
So essentially, with the end one, you can simply say while my iterator doesn't equal the end, do something.
Yes.
And then increment it each time. And when it finally does match the end, don't touch it. You've done every element.
I don't really understand what the STD begin and then
What's the point of them?
What's the point of them?
Yeah, not much.
Okay.
Yeah, so really the only difference, the only advantage these give you is that, as I say, they can work on built-in language. So C++ has this inherited from C, these what we call language arrays, raw arrays, C arrays, a few different names for them. But they're rubbish. They're problematic in lots of different ways. They're best avoided. Better to use these standard containers, and then you can always just do begin, and you never really have to worry about these things.
Those ones don't have their own .NET.
They don't have member functions because they're fundamental built-in types.
Just going back to when you said if I try to read or print out a value for container.end,
Yes.
what that you said that's undefined or throw an error.
It's what we call undefined behavior, so anything can happen. But we're going to talk
So
a
it
little.
wouldn't give you the last element of the vector or whatever it was.
No, because it's one past the last element of the vector.
It will either give you garbage random bytes, whatever happens to be in memory, or it will just.
So you can only use this container.end purely
As a marker to say, have I got here yet?
to the end.
Yes.
Or near the end.
That's its sole purpose, is to say, have I got here yet?
Are we done?
Are we done? Are we
Or
finished?
the actual last element you'll have to do, container dot element number. Or whatever.
You might be able to do .n minus 1.
For some containers. Yeah.
Can you remind the difference between capacity and size of the container?
Okay, yeah, so we're going to go over the containers a bit more next week, actually. But a vector and a couple of other containers, string, for example, has a notion of a capacity and a notion of a size. So the size is how many things are in my vector right now, and the capacity is how many things can I store before I have to go away and request some more memory from the operating system. So most of the time, like 99.9% of the time, you don't really have to care about the capacity because it's something that is automatically managed for you by the vector class. That's really the point of using vectors. It's because it automates all this memory management. When it runs out of space, it'll automatically go and get some more memory and use that extra memory that it's just got. The capacity you only really have to care about if you're doing really, really performance critical stuff where you absolutely must avoid any possible allocations, and then you want to do things like reserve up front or
Or if you're multi-threading and you're going to break the program, you can validate iterators and other threads, things like that.
The capacity is how many more things or how many things can I store until I have to reallocate.
To get it right on lines about iterators.
Oh.
If an iterator is just an address to a place in memory, and if you dereference the iterator begin, you get the value.
Okay, so a pointer is a memory address.
Oh, right, yeah.
A pointer is one kind of iterator, but it's not the only kind of iterator. So a better way of thinking about iterators, it's just like a position represents a position inside a collection.
Okay, so
yeah.
So should I think about it like an int or something? Like, is it like contains the value 0?
So an iterator doesn't contain the value; it represents something that points to the value. It stores an index, right? So we can have an iterator that points to position 0. We have an iterator that points to position 1. And we can modify this iterator so that it points to a different position. And we can, what's called, dereference the iterator to find the value of the thing it's pointing to. And we can even modify it so that it points just off the end of the container, that's the end position, as we call it.
Sounds to me similar to pointer.
It's
So what else could be iterator apart from pointer?
Okay, so a pointer is a valid kind of iterator. It's, in fact, the most powerful kind of iterator. We call them contiguous iterators. So that's fine when you've got what we call a contiguous array, linear array in memory. Right. So how a vector works, you just all your values are at the top diagram there. They're just next to each other in memory. So when you increment the pointer, you move to the next address in memory, and you find the next thing. But if you think about how a linked list works, if you're familiar with linked lists, okay, well, okay, a linked list is a different kind of data structure. It has quite different properties from an array or a vector. They're useful for particular kinds of problems. And with a linked list, you have what's called a node, and node holds the value of that node, and it holds a link to the next node. And these nodes form a chain, a linked list. So it's a list of values, each one of which holds a pointer to the next link in the chain.
Imagine it like this, a vector, right, so not a list, not what you just said, is like a row of houses, right? Everyone's a neighbour, they're all just next to each other. So if I had instructions for you, say visit these 4 houses, these 4 neighbours, just go, yeah, fine, this guy, this guy, this guy, and they're all next to each other, very simple, right? They're all close together. And then a linked list would be like a set of instructions where I've told you to go to this address on one street, and then another address halfway across the city, and then another address somewhere else. None of those people are neighbours, they're all just scattered. So if you imagine that the city is your computer's memory, then the 4 neighbours are nice because they're all close together, right? So in terms of the CPU, it's just we can bring them all at once. Whereas when they're this just all over the memory, randomly allocated somewhere, they're just scattered, it's got to fetch it from your RAM into the CPU. It's like, yeah.
So can you perform similar type of things on a linked list like a vector?
Yes.
You can.
You
So
can iterate over it.
that's
saying node 1, node 2, node 3.
That's a really good way of putting it. So yes, imagine that a vector is like, as Ollie says, a row of houses. And we know that each house is exactly the same size. So if we wanted to deliver a letter to the 4th address on this row, we don't even have to look at the house numbers. We just know, oh, each house is 20 meters wide, so we just have to walk 80 meters and we'll get there. Okay, with a linked list, it's as if we're delivering to addresses, but in order to get to the 4th address, we have to first of all go to the first one and say, okay, hi there, where's the next link? And they'll say, okay, well, you have to go up there and around the corner, and then you'll find, and then we go to the second one and say, okay, how do I get from there? It's like following a treasure hunt, yeah, following a chain.
So extend your analogy to breaking point. It's like going to each house, right? Going into the living room to get what you want, then going to the kitchen to find the address of the next house.
I suppose so, yes. Yeah.
Does a linked list have to be of the same type, or can it have multiple types?
All the collections are
Same type.
heterogeneous, as some people say. They all have the same type, yes.
You mean homogeneous? Homogeneous is the same.
Homogeneous, yes, yes.
So is it when I print out the addresses, vector, they are sequential numbers, but when I print out the addresses of
The elements in the linked list, they're going to be all over the place. They could be anywhere. Yes.
In memory.
In memory.
What they store. It's just they're scattered all over the place in terms of your computer's RAM, which makes them a bit slower to go through. But in terms of you as the developer don't care about.
So
you know it's arranged like that, so you know it's a little bit less efficient. But in terms of what you can physically do with them, you get the same functionality as a vector.
yeah. So why you say, well, hang on, that linked list seems really inefficient. Why would this ever exist? If I have to go to each address to find out where to go for the next one, that seems really inefficient.
You can have different parts of the code which.
It's not that. It's that think about what happens if we've got 1,000 links in this chain. Okay, so with our vector, it's a nice row of 1,000 terrace houses. With our linked list, we've got 1,000 houses, but they're all over the place, and we have to visit house 1 to find out where house 2 is, to find out where house 3 is, and so on. But let's say we want to insert a new house into the middle of the chain. Well, all we have to do with a list is to go to house 49, say, and say, okay, instead of redirecting people over there, I want to insert a new link to the chain. So redirect people there, and with the new one, you say redirect where the old one went to. So you can insert something into the middle of a list very quickly. Whereas with a vector, if you want to insert a new house in the middle of your nice row of terraced houses, you've got to go and demolish half your houses, build a new house, and then rebuild all the ones you've just knocked down. No. So inserting things into the middle of a vector is expensive computationally, but inserting things into the middle of a list is fast.
And removing as well.
And removing, absolutely. Yes, because to remove you'd have to demolish the house in the middle and then shift up, as in demolish the entire row and rebuild all the ones except the first. Yes, anyway, you get the idea.
The last element, does it have a pointer to itself?
In a linked list,
Yeah.
that's one valid implementation, or one implementation. There are a few different ways of doing it.
Before you expand the capacity of the
There-
list, then it will.
You don't expand the linked list, you just allocate a new thing and then say, here's the last one
Okay.
point to.
You do you have function like pushback or.
So it depends on what kind of list. You can have a doubly linked list. So each element points to the one in front of it and the one behind it. Obviously the front and the back have nothing, well, behind or in front. So if it's doubly linked, usually they implement it so that actually internally they can loop around. So you can stick it on the back, you can stick it on the front in constant time because you can just find it instantly. A singly linked list, like stood forward list, you can only stick it on the front unless you obtain an iterator to a particular element and then give it that.
I was planning on talking all about different containers and data structures next week. I thought, okay, today we're going to talk about iterators because they're like the glue between the things, but maybe I started in the wrong place. Maybe I should have talked about the containers first. Oh well, too late now. These are the slides we've got today. Next week's going to be an interesting talk, then, probably. Hopefully I will be less sick. Anyway, let's talk about iterators a bit more. What we can do with them, what they represent. An iterator represents a position in a collection. A house on the street or a house in the chain of houses. I like this housing analogy. If an element exists in this position, we say that the iterator is valid. If there is no element of that position, the iterator is invalid. So we've got the address of a house, but the house has been demolished. The house is no longer there. That's an invalid address. It's an invalid iterator. We can't have position 50 of a vector of 40 elements. So it's possible to have invalid iterators, iterators which don't point to something valid. And end is an example of that. iterators are value types. So again, we talked about it quite a lot. That in C++, we really like value types. They make our lives really easy. Value types, copying, assignments, all work the way you expect them to work. If we copy an object and we modify one of them, those two things are no longer equal. This is value semantics, as we talked about before, right at the beginning of Module 1, second lesson, I think. We talked about what it means for something to have value semantics and how all objects in C++, by default, unless you do special things, they have value semantics. And that's true for iterators as well. So we can copy iterators, and when we copy them, the new one points to the same element as the first one did. But if we modify one of those iterators, it doesn't affect the copy. And we can compare iterators for equality. Two iterators are equal if they point to the same position in the same collection.
So there has to be both. It has to be the same position and the same.
Yes. So if I have...
So they're not going to be equal by value by itself. It has to be the same.
The value of an iterator, if you want to think about it like that,
is that reference to that list?
Is its position and the collection it represents. Oh, sorry.
We should mention that iterators are not magically tied to the thing that they are pointing at. I.e., if you are using iterators to read stuff, like say you're iterating, right? And at the same time as using them, you modify the object. So, for example, you're going to come.
We're going to get into that. It's going to give people headaches right now. But let's just have a little look at what we can do with iterators. So, I've created a vector. Vector is a kind of collection, the simplest kind of collection in some ways. This collection has 3 things in it, labelled 1, 2, and 3 rather than 0, 1, and 2, which actually might have been easier, but still. Okay, and then I call begin, vec.begin. And this returns me an iterator which points to the first position in this vector. Points to element number 0 in this vector. I've used the auto keyword here, which is something that comes in very, very, very handy with iterators. Because the actual type of this thing, if you wanted to type it out, it's got a really, really long name. And it's really inconvenient to type out. And you almost never want to do that. Way back in the old horrible C++ 98 days, you'd have had to write it all out, and it's about 20 characters long. And lose the will to live. But with C++ 11, new C++, we can just say, I just want you to deduce this by yourself. Whatever type vec.begin returns, it1 is going to be an object of that type. So we can copy iterators. We can create this new object, it2, as a copy of it1. I can see there is a mistake on this slide. 2 seconds. Ninja editing, absolutely. So we can create a new iterator which points to the same place in the same collection. They both represent index 0 of this particular vector. So it2 denotes the same position in the same collection. And so we can assert that it1 is equal to, we can compare them for equality, we can say it1 is equal to equals it2. Because they're value types, copy, an assignment, an equality, comparison, they all work in the ways you would expect them to. So we can change which position an iterator points to. So now, it2 did point to position 0. It now points to position
3.
Just off the end. 3, yes, absolutely. So, oh, sorry, I'm in. Oh, you've got a whole other screen there. I can put my hand over this one as much as I like. Excellent. So now we're changing what it2 points to. We are changing the value of it2. So it now points just after the end of the collection. So two iterators are equal if they point to the same position, same index into the same collection. And now it still points into the same collection, but it points to a different index into that collection. So these iterators, it1 and it2, are no longer equal.
Plus the last IT2 is now invalid.
IT2 is now invalid, absolutely, yes. But we can still compare it. Say, are you the same as this other thing? This is pretty much actually the only useful thing you can do with invalid iterators, is to say, am I there yet? So we can assert that it1 and it2 are different. Here's a fun thing. What would have happened if my vector was empty? I've created a vector there with 3 things in it. What if I created a vector with no things in it?
Both point to the same place.
It would be invalid.
They would both point to the same place, absolutely. So begin would have returned me past the end iterator. Well, yeah, begin and end would return the same thing. In fact, that's how you can tell whether a collection has anything in it. If begin and end point to the same place, well, you know it's empty. And that's another reason why we have these off-the-end iterators, because it lets you do these checks for, it lets begin do something valid on an empty collection.
So it would have no elements if it was empty.
If it was empty, yes, it would have no elements.
So then how could you begin it? How could you use begin? Because begin it all points to the first.
Well,
You can't read or write it. You can still compare it to end if they're equal. You know it must be empty.
so begin points to the first thing, end points to one past the end.
But if
And as we
there is no
reduce the
element-
number, what we do is in an empty collection, begin returns the one past the end position.
It's always good to think about the base cases when thinking about these sort of things. Because they're like probably that's where the rules of these things come from, because they're all what's the word? It's like rules of mathematical rules of induction. That's how the
Yes,
these things turn.
exactly that. So actually, if vec was empty, all of these things would still work. Just this assert would not pass, because it1 and it2 would still be the same. And if that sounds a bit kind of weird, then maybe sort of stare at this for a while until you can think about why it makes sense.
Or accept it then.
Well, that's also an option, I guess.
But if there's nothing there, you can't get anything, right?
Yeah.
It's all existential.
So an iterator represents a position in a collection. And we can say, all right, what currently exists at this position in that collection. So if I have an iterator which points to element number 0 of a 50 element vector, I can say, all right, what value is there right now? And it will return me a C++ reference, return me a reference to that thing, whatever value. So if the vector contained 1, 2, 3, 4, 5, 6, 7, 8, 9, blah, 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 then dereferencing an iterator to position 0 would give me the value 1. It returns whatever is at that position right now. So if I then went and changed the value by doing vec square brackets 0 equals 99, dereferencing that same iterator would now give me 99. Yes. This operation, this saying to the iterator, go and fetch me the value that you're pointing at, it's rather confusing. We call this dereferencing the iterator. Even though it gives you back a C++ reference, the operation is called dereferencing. There are reasons for that, but it's a bit surprising and confusing, but it's just the terminology. Sorry. That operation of going and fetching the thing that the iterator is currently pointing to, that's called dereferencing. And to perform a dereference operation, we write star, asterisk, and then the name of the iterator. So if you're familiar with pointers, yes, this is exactly what we do with pointers to obtain the thing the pointer is pointing at. So this operation, star iterator, dereferencing operation, gives you the value that it's currently pointing at. More terminology. I said there would be lots of terminology today. If the returned reference, that is, if the thing we get after dereferencing, if that is read-only, then what we have, the thing we've dereferenced, we call it a const iterator. We'll return to const iterators. Well, we might not now because we started late and I've talked a bit too much. But anyway, if the return reference is read-only, it's a const iterator. It's an error to dereference an invalid iterator. So if the iterator points to a position in a collection that is not valid, then attempting to see what is there is an error in your program. Or perhaps put it another way, if it's pointing to a collection which has disappeared, been deleted, attempting to see what is in this deleted collection is an error because it doesn't exist anymore. An iterator represents a position and a collection. So we could have a 10-element vector. If you just forget about iterators a minute and just think about indexes, ints. I can have sort of the abstract notion of position 50 in my 10-element vector. But saying to the vector, okay, go and give me the thing in position 50, that's going to be an error, right? Because there aren't 50 things in my vector. Well, an iterator is just a position, an index that knows the collection that it represents. So we can form an iterator, try and form an iterator to position 50, but dereferencing that iterator is going to give us rubbish.
So is one of the valid use cases for using a dereferencing an iterator is to use it multiple times in your code somewhere else, rather than having to reassign or say, oh, iterate this equals this element.
Well,
this equals this element. You can
dereferencing the iterator is how we do anything really useful with it. Right? Because at the end of the day, when we want to sort a container, say, let's just start much more simply. Let's say we want to, from the examples last week, we want to count I've got this vector of numbers. I want to count all the numbers that are equal to 3. Well, in order to do that, I have to look at each element and see, is this element equal to 3? And how do I do that? Well, I have to dereference the iterator to find out what the value is at that position.
Probably worth mentioning that explicitly that the iterator is not that.
Sorry? The iterator is not the value of the element. No. The iterator points to a position, points to an element.
What methods has it got?
An iterator? Well, this is what we're going over now.
That's like done. That star is done by operator star, right?
Yes. Yes. An iterator need have no member functions because a pointer is a valid kind of iterator. So they're all done using these
Okay.
operator overloads. So to show you an example of what I mean by this dereferencing operation, again, we form an iterator to the start of the vector, to position 0. So if I dereference my iterator and print it out, print out that value, what am I going to get? What's it going to print here?
1.
1. Exactly. It points here. So when I say, okay, what is there? Well,
But why do you need to dereference it with the star? Why couldn't you just say it1? It would have still printed 1.
Let me just give you the address.
yeah. The iterator is not the value. An iterator represents index 0 of this particular collection.
If you did that, we'll just return memory address.
I think this would probably be a compile error. If you didn't have the star there, if you just tried to print it1, there is no, you can't print an iterator. It's sort of meaningless. You could try and print the address of the iterator, but that's not going to be of any use to you whatsoever. That's just going to be some stack address. What, printing an iterator itself? No, you can't. No.
You can add it to access the address, right?
Hmm?
You can add to
Sorry, I can't hear you very well.
you can add an ampersand to access the address, right?
Well, you can, but that, again, wouldn't be at all useful to take the address of an iterator. An iterator is just an object. It's an object that represents this notion of a position within a collection. And when I say I want to dereference it, I'm saying to the iterator, okay, go and, you know which collection you are looking at, you know which position you're looking at, go and tell me the value of the thing at the position you represent in the collection you represent. Go and fetch me that value now. So we can also do this. Do you know what? I'm just, I'm not sure that I can very much. I'll try it. Apparently it really doesn't want to. I'm trying to bump it up. All right, gone too far. So if we dereference, this iterator points to position 0. If we dereference it, we get the element that's at position 0, which has the value 1. We can do it the other way around as well. We can dereference this thing, which fetches me a reference to that object, a C++ reference. Remember, dereferencing returns a reference. I know that's confusing. I'm sorry. I didn't come up with the terminology. I know it's mad. We dereference the iterator. It gives us a reference to that element of the collection. So we can change the value of this thing. We can change the thing is at position 0. So after this operation, what are the elements of my vector after this line now? 42, 2, and 3, absolutely. We have changed the thing at position 0 via this iterator. And if we do the same thing again, we dereference the iterator one more time and print it out again, we're going to get 42. Of course we are, because that's what we just set it to.
So saying dereferencing is essentially just saying get the value.
Yes,
And return it.
that's exactly what it is. It's called dereferencing because that's what it's called. I didn't come up with it.
No, fair enough.
Fetch the value would be a better way of.
It kind of makes sense, but yeah, it's just getting the value.
Yeah.
You might want to think of it as de-address, because it's turning an address into what's at the address.
Yeah, yeah, it sort of makes sense. But yeah, getting the value is easier.
Yeah.
Quick question,
Yes.
very quickly. So going back to it1, that's equivalent. So the vec.begin is equivalent to saying vec square bracket 0.
No.
Because that's what the value that's what's referenced. Vec.begin is referencing the value at vec square bracket 0, right?
No.
Square bracket
Oh,
0
why?
is the value. Sorry,
What is the reference?
Iterator's not the value point of it.
Dereferencing the iterator is the same as saying,
no, but
give me
why
the
you
thing
put
position
it
0.
there
Sorry?
in line, auto it1 is equal to vec.begin.
Yes.
Isn't that equivalent to saying it.1 is equal to vec square bracket 0?
No.
Why?
Because vec square bracket 0 gives you a reference to this thing. This gives you an iterator that points to this thing. That's not the same thing. In fact, quite different things, and that's one of the sort of the keys to understanding all of this weird iterator stuff. Okay,
So is it equivalent to vec?
vec.front would be the same as position 0.
With that bracket, just vec.begin.
Yeah.
Is it equivalent to vec? You like
No, that's a funny thing that C arrays do that vectors
no,
don't do that.
like I don't remember how you call it when you the reference to the first.
Yeah,
element
that's.
in,
I know what you're getting at. That's something that C arrays do, and that's
it was not partial in
yeah,
STL.
yeah. That's actually why we don't like C arrays. So because they have this thing called point to decay, so we just pretend they don't exist. Okay. So vec square bracket 0 gives you a C++ reference to the 0th element.
Yes.
Yeah. Vec.begin doesn't give you a reference, it gives you this thing called an iterator. Now, if you remember when we were talking about references, C++ references, I said it's like giving this object a new name, just a new way of accessing it, a new name to access it by. Okay? An iterator is not the same thing as a reference. An iterator is an object, it is a value type. It's an object, you can think about it as an object that's a struct that contains reference to the container and a position. So think of it as like an int and a vec reference. And when I do the dereference operation, it does, okay, now vec square brackets, whatever my index is. Perhaps I'll write that down. Might be a... This isn't, by the way, this isn't how iterators are implemented, but it's sort of a, you can almost think of it like this. So imagine that it's this kind of special object, a struct that contains an index and a reference to the container. Ignore that, ran out of room. So I don't know if you can read that at the back of the room. But you can imagine an iterator as being this object that holds an index and a reference to the container. In this case, I've said it's a vector of ints. And then we've got this, as I've written it here, this operator star. And when we call this operator star, then it goes and does the square brackets operator on its two members.
It doesn't work like that.
That is not really how it does it. It's how you can think about how it works.
So what's that int?
Int ref, that's supposed to be my version of an ampersand. I'm not very good at drawing them, sorry.
No one is.
No, they're quite hard. It's not something you draw every day, is it? Actually, yes.
Start to write.
Mine just looks like eggs with a bit of a tail on it. Anyway, the important thing is not how I've drawn this ampersand or done it badly. The important thing is the difference between a reference into a container, which is what you get when you with the square brackets operator, and an iterator, which is an object in its own right. An object that represents an index and the collection that is. Does that make more sense as to why? So .begin returns you an object of this type. So if I call .begin, it's going to create this object. It's going to set idx to 0 and vec to whatever object you call it. You don't seem entirely convinced on
No,
this.
I've understood it better than 4 years with me in this detail.
Okay, so while we're doing this, let's have a look at a very similar case, except I can't spell int. I don't know why I've given it a capital I there. Let me correct that. I've no idea why I did that. Anyway. So now exactly the same as I had before, except now I've got a const vector. I've got a read-only vector. And again, I can get an iterator to the start of this array, start of this vector. And I dereference this iterator, and what's it going to do? What's this line going to do? Yeah, it's not a trick question.
You got the wrong vector.
I've got what, sorry?
You're using the wrong, because your new vector is called C vector, and I don't think your relative changes that.
Oh yes, sorry, you're absolutely right. That's what you get for copying and pasting. So it was a trick question, but unintentional trick question. Yeah.
You won 3 tickets for the next class.
Yes.
You too.
Yeah. Okay. So you're right. We an iterator into this CVEC now. Yes, right. And we dereference it, and that prints 3. Because this represents the thing at position 0. We dereference it, it prints 3. I don't like this slide. keep seeing mistakes on it. Every time it prints, it gives me one line in advance, and I see the next one, and I'm like, oh, I got that one wrong. But now, if we dereference it and try and set it equal to 42, well, now we've got a problem. Because up here, when I declared my vector, I said that it was const. I said that it was read-only. So when we have a const variable, what does it mean? It means it cannot be changed once it's been initialized. So I've initialized this cvec to hold 3, 2, and 1, and that's all it can ever contain, because it's now const, now read-only. As soon as I've finished initializing it, it is unchangeable for the rest of the life of my program, till it gets destroyed. And what I'm attempting to do here is to change the value of one of my elements. And so quite rightly, this is going to say, no, you can't do that. Because this const is a promise that it's not going to change. It's a guarantee that it's not going to change once it's finished initializing. So obviously, I cannot then later go and change it. So in this case, the type of int2 is a const iterator, an iterator to a const container. An iterator which does not let you modify the values. You can only read them. Last little one on this dereferencing. Oh, well, it3. I set it equal to vec.end. Or cvec.end, it really doesn't matter. And then I dereference it and print out. What's it going to print?
Error.
Is it going to print error?
Some garbage, right?
It's going to print some garbage, yes. What it's going to give me, in this case anyway, is whatever happens to live at this address, which is probably going to be meaningless garbage. It might crash. It might, if you've got a standard library that does nice things, it might give you a nice error message saying you've run off the end of your vector, you've dereferenced the end iterator. It might give you junk. It might crash. It might do anything. If you try and do this in your program, it's no longer a valid C++ program. Scary, isn't it? You put it like that.
Very nice number. 32630.
Right, okay. If you run it a few more times, does it give the same number every time? Yeah, so attempting to dereference the end iterator is a mistake, don't do it. It may print junk, may crash, may give you a nice error message. If you're really unlucky, it'll just print 4, and you'll never even notice that something's wrong. So we can dereference an iterator, we can say, okay, what lives there?
I have a question.
Yes.
If you were iterating over a smaller file of a larger vector,
Yes.
and 4 was the next one,
Yeah.
then it would return 4.
Yeah. Because it's still a valid iterator. Yeah. In that case, yes.
Yeah.
Okay, so the other things we can do with iterators, the other operations we can perform on iterators, we can increment an iterator to move to the next position. So we call .begin, we get an iterator that points to position 0. When we increment that iterator, it now points to position 1. So if you think about that little thing, we're changing the IDX member to be 1 now instead of 0. And then we increment it again, and it points to 2, and it points to 3, and it points to 4, and it points to 5, and eventually it's going to point to whatever the end iterator has. And at that point, we know we're finished. iterating. So valid operations with iterators, we can dereference them, we can increment them. The way we do this, the way we write it, is we write plus plus iterator. So star iter dereferences the iterator, plus plus increments it. So this is the same operator that's used for ints. To increment an int, we've got an int with value 1, you do plus plus int, plus plus I now has value 2. Some iterators can be decremented. Next slide. And as with ints, there are both, as we call them, prefix and postfix versions of plus plus. You generally always want to use this first one. The postfix version exists as well and does roughly what it does for ints, but it can sometimes involve a copy, so it's better not to. Use this one. Plus plus iter moves the iterator, advances the iterator, increments the iterator so that it points to the next position. And there is a standard library function, it's called standard next. It returns you a new iterator, which points to one place after iter. Doesn't modify iter, gives you a new iterator that points to the next one. It's quite useful, surprisingly.
Sorry. When you do the start and the beginning on iterator images, are they tied to only one object? Or you can just swing it back already?
So I didn't really catch.
So I was saying, like when you have these iterators start at the beginning and end, like,
Yes.
they can point to any kind of type. They're not stuck to the one thing you're looking at currently.
They can point to any position of a collection of the same type. Yeah.
And potentially the same collection type.
Collection type is what I meant, yes.
They don't have that inheritance thing, do they? Like,
There is no inheritance involved whatsoever.
so I can't point to, like, if I derive class a vector using a vector point. If using a vector to iterate.
No, that won't work.
The right requirement is the collection type of the collection.
Yes.
But you can't use it has to be a vector of int. It could be a vector
Yes,
of
an iterator into a vector of ints cannot be reassigned to point to an element of a vector of floats.
or a forward list of it.
Yes, or a standard unordered map or whatever we might have, yes.
When you're writing iter here, are you just
That's imagine it's an object of some iterator type.
Okay, so you can just, it could be anything.
Yes, that's just the name of an iterator object. Is your hand up, or you?
It is up, I
Oh.
know. Sorry, just stretch it.
Oh. Well, let's have a bit of variety and fed up with vectors of ints. This time we've got an array of 12 floats. So standard array, I mentioned this last week. Standard array is another data structure that's in the standard library. Unlike a vector, which has a variable size, we can grow and shrink. An array is a fixed size. In this case, always going to contain 12 floats. We haven't initialized it, so all my floats are equal to 0, but there are 12 of them. There have to be 12 of them, always 12, because that's what I've said. But an array is a container. We can get an iterator to the 0th element. So now, it1 points to the element of position 0. Plus plus it1. So, it1 now points to the element at position 1. We have incremented the iterator. We haven't changed our container in any way. We haven't modified the container. All we've said is that instead of pointing to index 0, as you did there, now I want you to point to the thing at index 1. So we've modified the iterator, we haven't modified the container. I've done something slightly different. Created a new iterator, it2, and I've used this standard next function. So standard next, well, I just said it actually.
I'm very sorry to say that isn't quite.
What is?
You won't get zero initialization of any floats.
What if I put in another empty set of...
If T is not something that has an explicit default constructor that will do something, then it's as if you initialize a C array, and I just tested it to check.
Okay, what if I put another empty set of empty...
Oh, if you then do aggregate initialization.
Yeah, okay, right, well, fine, to keep Ollie happy. All right, what if I do this?
Where's the common legal?
Try it.
Okay. I believe it.
I believe it is. Yeah. Right. This is saying initialize the first thing to 0 and then initialize all the other things to 0 as well. Yes. Okay. So we're now using the standard next function. So can anybody tell me what this is going to do?
Exactly the same as plus plus it1.
Exactly the same as plus it1, Sassad. Probably tell from my tone of voice I'm not 100% convinced.
What's going to give you an iterator to the next element?
Exactly that, yes, that's right. So you can see with this auto, it's going to create a new object. So it's going to create an object that points to the element at position 2. But iterator 2, sorry, can tell I was like not really with it today when I was writing these slides. So it2 now is a new object, a new iterator that points to the element of ARR at position 2. But it hasn't modified it1. That still points to the element of position 1. It hasn't changed it1. So, here's a question. Assuming I've typed it correctly, which I actually haven't. God damn it.
Also, I lied. It was completely fine with it
At least
So it was fine as it was. They were value initialized. Excellent. That's yeah, good. All right. So what's this do?
Makes every element 99.
It says every element of my array, all 12 of them, to the value 99. So why does it do this? Well, let's think about how the for loop works. This 3-element for loop. First of all, we call this first guy up to the first semicolon. So we create a new object called it, and we set it equal to arr.begin. So it is now an iterator to position 0. And the next thing it does is first of all, it runs the comparison. So it says, is it equal to 1 past the end of my array? Oh, sorry, is it not equal to 1 past the end of my array? So if the two are not equal, then the test returns true, so we enter the body of the loop.
Shouldn't that be dereference the its and the end of the array?
There?
Yeah. Should okay. No, I answered the question. Thank you.
No. So first of all, we set it equal to the begin. We test whether it's the same as the end iterator. So if begin and end return the same thing, if an array can't be empty, but if it was a vector that was empty, if begin and end return the same thing, our container was empty, would be empty, we'd never enter the body of the loop. So within here, doing this dereference is perfectly safe because we've checked that we are not at the end. So we dereference it when it points to position 0. We dereference it to get a reference. I know, I'm sorry. We dereference it to get a reference, and we set that element to equal to 99. We go down to here. So at this point, our array is going to be 99 followed by 11 zeros.
And what's the difference with the formulation with the column?
With a range for loop, I'll talk about that. I just want to show you this 3 element. Okay, so we get to here. At that point, we execute this part of the loop header. So we plus plus it. We increment the iterator. So our iterator did point to position 0. It's now going to point to position 1. And again, we say, okay, well, is position 1 off the end? Well, no, it isn't yet. So we set the element of position 1 equal to 99. Then we increment the iterator and we test, is it equal? And eventually, we're going to increment our iterator and we're going to reach the end of our array. We're going to compare, and our iterator is going to be equal to the end. And at that point, we stop our iteration and we continue with whatever code we've got. This is why these things are called iterators, because we use them to iterate over our container. This formulation in a for loop. Set a thing equal to begin, test it, that it's not equal to end, and increment. This is basically the basis of all of the algorithms. This will work for any kind of iterator that you like. I've used an array iterator here. It'll work for a list iterator, for a set iterator, for an unordered multi-set iterator, multi-map iterator, whatever. This formulation here is how iterators get used. Yes, sorry.
Do these dot begin and dot end the only types of functions that return an iterator? Or can be used? Because at the start you said iterator is not a type, but then you're using auto and saying that dot begin and dot end.
Stood find returns an iterator if you use it on. Or if you use it on. But you can use stood find to find particular elements, and you get an iterator back. But it might be the beginning. It might be the end.
But the interesting say at the start, right at the start, an iterator is not a defined type. It's a concept that we use to say
okay. So dot begin is going to return you some type that adheres to the iterator protocol, that behaves like an iterator.
Yes.
Okay?
Which is
but an array iterator is not going to be the same thing as a vector iterator. It's not going to be the same type. It's going to have the same properties. You can do the same things with it, but it's not the same type.
It's basically a class. Okay, all iterators are just
not that, but what I'm saying is, what are the, let's say, this begin and end the only functions to different return an iterator type?
Okay, so many of the algorithms,
from a collection.
many of the algorithms actually, as Ollie says, return iterators. So there's an algorithm called binary search, which returns you a position, returns you an iterator into the collection, for example. If you're writing your own types, well, you could, instead of calling it dot begin, you could have a function called dot start that returns an iterator if you wanted to. But this dot begin and dot end is the convention used by the standard library, and obviously is what you should follow with your own types. Calling it dot start would be stupid. Don't do that.
So when you use like operator, when you use plus plus on an iterator, or plus 5 or minus 5, whatever, that's just calling operator plus or operator minus or whatever operator overload, right, on that class, and it returns, if it's the plus operator, for example, you get a copy of yourself, your own, its own, the iterator's own type gets a new copy created and returned, except it's pointing 5 things ahead. That copy is returned pointing 5 things ahead if you hit plus 5. So you can implement your own iterators. You can do it. And
Yes.
You can make them compatible with
Yeah.
the standard library. They're just classes with operator overloading.
And just as a final note, because Laurent asked, what's the difference between this and a range for loop? A range for loop is a special. When I introduced them, I said, well, things that adhere to this container protocol, this container concept, we can use them in a range for loop. And what I really meant by that was that they have begin and end functions that return valid iterators. So when we write a range for loop, the compiler translates it into something that looks almost exactly like this. It does this, so it just saves you having to write it out longhand. So convenience, but it's doing exactly this. Anyway, we're now way past time, and I've just been nattering the whole time. I'm sorry, it's been a very boring session probably. But it is 7 minutes past 9, and we should probably draw a close to it. It's pretty hardcore today, wasn't it? Lots of good questions. But yes, people are itching to go home, I'm sure. Or go to the pub, or go to wherever you're going. So I guess we'll pick it up next week, and next week's going to be the last one before Christmas. So yes, thank you all for coming. And you've all gone very quiet. I don't know, you're probably just all a bit shell-shocked after that, but yes. Or you're going, oh my god, iterators are amazing, where have they been all my life? I'm a convert. All right, thank you very much. See you next week, I hope.
Thank you very much for Tristan for the